I am Dr. Basir-Ahamed-Khan, Assistant Professor of Physics, Krishnath College. This is lecture 1 of module 11. In module 11, the name of the topic is behavior of real gas. In that module, I will discuss the topics that are deviation from ideal gas equation, Andrew's experiment on CO2 gas, critical constants, continuity of liquid and gaseous state. Next, about vapor and gas, then boil temperature, Van der Waals equation of state for real gas, then values of critical constants, comparison with experimental curve, and lastly PV diagram. Today, in my first lecture of module 11, I will discuss with the point deviation from ideal gas equation. I already said that the name of the topic of this module 11 is behavior of real gas. So question arises, what is the deviation of real gas from ideal gas equation? We know that the ideal gas is a special case of real gas under the condition that when the pressure is very low and temperature is high, then real gas behaves as an ideal gas. So to specify a system, we need thermodynamic variables. For gaseous system, we need three thermodynamic variables: pressure P, volume V, and temperature T. Therefore, for ideal gas equation, we know that PV equal to RT. PV ideal gas equation, PV equal to RT for 1 gram mole of gas. Here, if plot this equation, here is pressure P and volume V, then we get this type of curve. Suppose this is T1 and this is T2. This is the plot of this ideal gas equation, PV equal to RT. Here obviously T2 is greater than T1. These are the isothermal curve, and this is true for ideal gas equation. Now we know that we consider ideal gas when we assume the interaction between two gas molecule is negligible. For ideal gas, we assume there is no interaction between two gas molecule. There is no interaction between two gas molecules or with the vessel So there is no interaction between two gas molecules or with the vessel. And next point is that for ideal gas, we assume the gas molecules are point particle. The gas molecules are molecules are point particle. Molecules are point particle. That is point particle. That is they have no volume. That is they occupy no volume. They occupy no volume. This is no volume. This is the these are the assumption, and under this condition the gas is called ideal gas. There is no interaction between two gas molecules or with the vessel, and the gas molecules are point particle, that is they occupy no volume. But in real gas we know that there are interaction, attraction or repulsion between two gas molecules, and secondly gas molecules occupy volume. So it is obvious that the equation, ideal gas equation and real gas equation will be different, because the pressure and volume will be different for ideal gas and real gas. So pressure depends on the interaction between the gas molecules and the vessel of the gaseous system. So that's why it is clear that ideal gas equation is different, will be different from the real gas equation, because in real gas the gas molecules occupy volume, whereas we assume in ideal gas the gas molecules have no volume. And next point, in ideal gas there is no interaction between two gas molecules, but we know that for real gas there is an attractive or repulsive force between two gas molecules or with the wall of the vessel of the gaseous system. So the ideal gas equation and the real gas equation will be different. These are the deviation from deviation of real gas from ideal gas equation, or ideal gas from real gas equation. Now the second point is Andrews experiment on CO2 gas. That means Andrews experiment on real gas. Here we plot PV diagram at different temperature. In my previous figure, suppose this is figure 1. This is figure 1. In this figure 1, these are the isothermals. These are the isothermals. That means at every point PV the temperature is same, that means T1, and this is another isothermal at temperature T2. At the same way I plot PV diagram for real gas for Andrews experiment. At the below, the last one, I said A, B, C, D line. A, B, this is A, this is B, this is C, and this is D. A, B, C, D line at temperature 13.1 degrees centigrade. Next one is another isothermal at temperature 21.5 degrees centigrade, then 31.14 degrees centigrade, and lastly 48.1 degrees centigrade. There are 4 isothermal in this plot. The last one I explain the curve A B C D curve. That means the isothermal at 31.1 degree centigrade curve A, B, C, D, C and A, B and C, D. Okay. Now here we consider the isothermal at 31 degree centigrade. It consists of three parts. It consists of three parts. This curve A, B, C, D, A, B, C, D curve consists of three parts. Consist of three parts. One is AB part, then BC part, and then CD part or CD line, AB line, BC line and CD line. In the region AB, pressure increases if we go through A to B, if we go through A to B, in this region pressure increases and volume V decreases, and this goes to up to the point B. Next, at B, liquefaction of the gas begins. When we go from A to B, then pressure increases and volume decreases. Suppose we consider a gaseous system. Suppose we consider, this is for an example. I just, here is P, I create pressure and then volume will decrease. And this is shown by the line A to B. Now at B, at the point B, and another thing occurs. The gas begins to liquefy. As long as liquefaction continues, the pressure remains constant. As long as liquefaction continues, the pressure remains constant. That means by the line BC, if we go to B to C, the liquefaction continues and the pressure remains constant, but the volume decreases. Here is a very interesting thing. When we start from B to C, the liquefaction of the gas starts and it continues when the pressure is constant and volume decreases. The horizontal portion BC indicates this fact. Clear? When we go from B to C, pressure is constant but volume decreasing. This happens because the gas starts to liquefy. Now at C, all the gas is condensed. Now at C, this position, all the gas is condensed into liquid. Okay, the almost vertical rise of the portion CD. Now this curve CD, almost vertical line, indicates that the liquid is highly incompressible. The liquid is highly incompressible. So I repeat the curve ABCD. ABCD curve consists of three portions: AB, BC and CD. If I start from A to B, going through this line, here we see that the gas, the pressure of the gas increases and volume decreases, as it usual case, as expected. That means if we increase the pressure, the volume of the gas decreases. Now at the point B, another things occurs, because if I see the line BC, that means the horizontal line, the pressure from B to C, the pressure remains constant but volume decreases. It happens due to the gas is liquefied. The gas is turns into liquefied from gas to liquid, and this horizontal line indicates the gas starts to liquefy, and at the point C, all the gas is turned into liquid, and after that the horizontal curve CD, from here we see that all the gas is liquefied, and the portion CD indicates that the liquid is highly incompressible, because if we create large pressure, the volume change is very small. That means this is happen only for the liquid. So the isothermal, the next point, the next isothermal at 21.5 degree centigrade, 21.5 degree centigrade. Next point is 21.5 degree centigrade. Here this is this isothermal has the same nature. This is also the same nature of ABCD line, only here the horizontal portion is shorter. That means this is the horizontal portion BC, and here the horizontal portion is, here the horizontal portion is this. This is shorter for higher temperature. That means for 21.5 degree centigrade, the horizontal portion is shorter than the isothermal at 13.1 degree centigrade. The horizontal portion, next if I see this isothermal, the horizontal portion just disappear. The horizontal portion just disappear at the temperature 31.14 degree centigrade. That means the specific volume of the vapor just before condensation is equal to that of the liquid after condensation. Here I repeat this point. The horizontal portion just disappear for the curve, isothermal curve 31.14 degree centigrade. This means the specific volume of the vapor just before condensation is equal to that of the liquid after condensation. Okay, the point P, suppose if I suppose if I name this point P, the point P where the gas transform into liquid is called critical point. Transform into liquid is called critical point, and here the specific volume of the vapor just disappear before condensation. Specific volume of the vapor just before condensation is equal to that of the liquid after condensation, and this point is called critical point. That means liquid and vapor is before condensation and after before uh, condensation and after condensation is the same for liquid and vapor. Above this temperature, that means for 48.1 degrees centigrade, at this temperature the isothermal, the horizontal portion is absent in all the isothermal greater the temperature of 31.14 degrees centigrade. That means all the isothermal which are where which are temperature greater than 31.14 degrees centigrade, there are no horizontal portion of the isothermal, and as we increase the pressure and volume, the volume decreases but no liquid is formed. Here if I increase the pressure for these curve, and this curve, and this curve, if we increase the pressure, there will be no liquefaction occurs. We increase the pressure, volume decreases and it behaves like gas and no liquid is formed. At still higher temperature, the curves have almost the form of rectangular hyperbola. That means with the same as the isothermal of this isothermal and this isothermal. So if we take the higher temperature isothermal greater than 31.14 degrees centigrade, that means for these are the similar with the isothermal of this and this. Now these are the experimental view or experimental study of Andrews experiment on carbon dioxide gas. This is the experimental study or PV diagram of Andrews experiment on carbon dioxide gas. Now I say about the critical point. What is the critical point? Critical point occurs in particular experiment for carbon dioxide gas. The critical point shows for isothermal at 31.14 degree centigrade, 31.14 degree centigrade for carbon dioxide gas, for CO2 gas. At this particular point P, or at this particular point, critical point, there are no horizontal portion of the isothermal, and the special character is that at this point the specific volume of the vapor just after just before condensation is equal to that of the liquid after condensation. That means when, if I consider the curve ABCD, when B, at the point B, the gas turns into liquid, that means vapor, and if I increase the pressure, the vapor changes to liquid. But at the point P, there is, if I increase the pressure for this particular point, the vapor specific volume before condensation is just after the condensation of liquid. This is the special character of the particular point. That means, and again, if I increase the temperature of carbon dioxide gas and plot PV diagram, then there will be no horizontal portion, and this upper curve, that means this upper curve, this and these upper curves are rectangular hyperbola, similar as the ideal gas isothermal, or similarly ideal gas PV diagram. Now the critical temperature, critical pressure and critical volume, the critical constants, critical constants, critical constants. Critical constants, one is the temperature, pressure and volume of this, the temperature, pressure and volume of the point, the pressure, temperature and volume of the point, the pressure, temperature and volume at the point P is known as critical pressure, critical volume and critical temperature. The pressure, volume, pressure, temperature and volume at P is called pressure, temperature and volume at P is called critical pressure, critical temperature and critical volume. Critical temperature, and critical volume, critical volume, critical volume, critical volume. Now we define what is critical pressure, critical temperature and critical volume. First one is critical temperature. First one is critical temperature. Critical temperature. Critical temperature is a temperature below which the horizontal portion appears, and after critical temperature, greater critical temperature, there will be no horizontal portion and there is no occurrence of vapor or liquid. This is the critical temperature. I write the expression of critical temperature. It is defined as the maximum temperature, maximum temperature, it is defined as the maximum temperature at which a gas can be liquefied, at which a gas at which a gas can be liquefied by the can be liquefied can be liquefied can be liquefied by the increase of liquefied liquefied by the increase of by the increase by the increase of pressure alone, by the increase of pressure alone by the increase of pressure by the increase of pressure alone by the increase of pressure alone. Above this temperature, the gas cannot be liquefied, however large and applied pressure may be. Above the temperature, 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 the gas cannot be liquefied. The gas cannot be liquefied, cannot be liquefied cannot be liquefied by the however large the applied pressure, by the pressure. The gas cannot be liquefied by the pressure, whatever the pressure may be. Whatever the pressure may be. Whatever the pressure may be. That means critical temperature is the defined as the maximum temperature at which a gas can be liquefied by the increase of pressure alone, and above the temperature the gas cannot be liquefied by the pressure, whatever the pressure may be. Now the critical pressure, second one is critical pressure. Critical pressure. Critical pressure, the pressure necessary to liquefy a gas at critical temperature. The pressure necessary the pressure necessary to liquefy a gas liquefy a gas at critical temperature critical temperature is called critical pressure, is called critical pressure. Critical pressure is called critical pressure. Then critical volume. So critical pressure is the pressure necessary to liquefy a gas at critical temperature is called critical pressure. Now critical volume, now it is a volume which Unit mass of a gas, it is a volume which unit mass of a gas, unit mass of a gas, unit mass of a gas occupies at the critical temperature and critical pressure. Occupies at the critical temperature and critical pressure. Critical temperature and critical pressure. This is the critical volume. That means the volume which unit mass of a gas occupies at the critical temperature and critical pressure. This is the critical volume. Now the vapor and gas. What is the vapor and what is gas? Vapor and gas, in my next class I will talk about the vapor and gas.